April 1, 1943, 22,000 feet above Saint-Nazaire, France. First Lieutenant James Ward felt the B-17F All-American shudder violently as something massive struck from above. The sound was wrong, not the familiar crack of flak or the metallic snap of fighter bullets, but a deep, grinding roar that vibrated through the bomber's aluminum skin like a bandsaw cutting steel. Through the cockpit window, Ward saw a German Messerschmitt Bf-109 tumble past in slow motion, its left wing separated, pilot already gone. The fighter had collided with All-American during its attack pass, its propeller chewing through the B-17's fuselage like a circular saw through plywood. Behind Ward, where the radio compartment should have been, there was sky. The aircraft was cut nearly in half. The tail section remained attached by structural longerons on the left side and control cables running through what little fuselage remained. The right side of the aircraft was gone, simply gone, leaving a gap 6 feet wide that exposed the bomb bay, ammunition compartments, and tail gunner's position to 300-mile-per-hour wind. Through that gap, Ward could see the English Channel 22,000 feet below. Every engineer who'd helped design the B-17 would have calculated the same thing: structural failure imminent, catastrophic breakup inevitable, crew survival impossible. The aircraft should have folded in half and fallen from the sky in seconds. It was already dead. It just didn't know it yet. Ward did what any pilot would do when facing certain death. He kept flying. What happened over the next 3 hours would redefine understanding of aircraft structural integrity, pilot determination, and the engineering margins built into the B-17 Flying Fortress. Ward's crew would remain at their stations in an aircraft that was literally breaking apart in flight, would jury-rig repairs using materials never intended for structural support, and would coax a mortally wounded bomber across 400 miles of occupied Europe and open ocean. The Germans who witnessed All-American limping toward England reported an aircraft that shouldn't exist, a bomber flying with its fuselage severed, held together by hope and physics that defied calculation. Luftwaffe pilots attempting to finish the crippled aircraft discovered something terrifying. Even when cut in half, the B-17 wouldn't die. This is the story of how one pilot's refusal to accept the inevitable, one crew's determination to survive, and one aircraft's over-engineered construction combined to create the most improbable successful landing in aviation history. It's a story about the moment when human will exceeded mechanical limits and somehow won. And it begins with a collision that should have killed everyone instantly. The mission that went wrong. The 97th Bombardment Group had launched from Alconbury, England at 0830 hours on April 1, 1943, tasked with bombing U-boat pens at Saint-Nazaire. The target was heavily defended. German intelligence knew the Allies were desperate to stop submarine operations in the Atlantic, and Kriegsmarine had positioned extensive anti-aircraft defenses around the submarine facilities. All-American was flying in the high squadron position, third aircraft in a 12-plane formation. The bomber was relatively new, delivered to the 97th in February 1943, bearing serial number 41-24406, accumulating just 47 combat hours. The crew was experienced by April 1943 standards, having survived 8 previous missions without major damage. First Lieutenant James Ward, pilot, age 24, from Chattanooga, Tennessee. Second Lieutenant Kenneth Bragg, co-pilot, age 22, from Dallas, Texas. Navigator, Second Lieutenant Harry Newsell. Bombardier, Second Lieutenant Elton Conda. Flight Engineer, Technical Sergeant Dewey Burrell. Radio operator, Technical Sergeant Michael Zook. 7 other crew members filling gunner and observer positions. 10 men total, average age 23, flying a bomber that cost $250,000 to build, about $4 million in modern currency. The bomb run over St. Nazaire proceeded normally until the formation turned for home. German fighters had been harassing the formation throughout the mission, standard procedure for targets this heavily defended. Me-109s and FW-190s made repeated passes, forcing gunners to expend ammunition at rates that concerned Ward. By the time All-American cleared the target area, the aircraft had logged 73 separate fighter attacks without sustaining critical damage. The 74th attack was different. Oberleutnant Werner Girth, flying Messerschmitt Bf-109G4 of Jagdgeschwader 2, positioned for a standard attack from above and behind, the classic bounce that exploited the B-17's weak defensive zone between the tail gunner's arc and the ball turret's limited elevation. Girth's wingman was slightly ahead, drawing fire while Girth lined up his shot. What happened next was never fully explained. German combat reports suggested Girth misjudged closure rate or underestimated the B-17's size. American witnesses believed turbulence from preceding aircraft disrupted his approach. The result was unambiguous. Girth's Bf-109 struck All-American from above at a combined closing speed exceeding 400 miles per hour. The fighter's propeller contacted the B-17's fuselage directly behind the cockpit, cutting through aluminum skin, structural frames, and interior bulkheads before the impact twisted the 109's nose downward. The fighter's left wing separated, its fuel tank exploded, and the aircraft disintegrated. Girth never escaped. His body was later identified in wreckage recovered from French farmland. All-American absorbed the impact and continued flying. Continued flying with a wound that would have destroyed any other aircraft instantly. The damage assessment. Technical Sergeant Dewey Burrell, occupying the flight engineer's position behind the cockpit, had the best view of the damage. When the 109 struck, Burrell was thrown against his station as the fuselage buckled. He stood, looked aft, and saw France through the middle of his aircraft. The collision had severed the fuselage immediately behind the radio compartment. The structural damage was catastrophic. Right side fuselage skin, completely removed from cockpit to tail section, approximately 20 feet. Structural longerons severed on the right side, damaged on the left side. Bomb bay roof torn away, exposing bomb racks and ammunition stores to airflow. Horizontal stabilizer supports partially severed on the right side. Vertical stabilizer damaged but intact. Control cables partially severed, redundant systems maintaining minimal control. Oxygen lines severed, pressurization lost. Hydraulic lines damaged, landing gear control compromised. Electrical systems partially functional despite exposed wiring. The tail section remained attached by approximately 30% of normal structural connection, the left longerons and control cables that ran through the fuselage's port side. The attachment was so tenuous that crew members could see the tail section moving independently, flexing up and down as airflow buffeted it. Radio operator Michael Zook, positioned directly behind the point of impact, should have been killed instantly. He survived because he'd moved forward to communicate with the cockpit seconds before the collision. When he returned to his station, he found his position no longer existed, replaced by open sky and screaming wind. Bald turret gunner Sergeant Samuel Sarpoulis, suspended beneath the aircraft in his rotating turret, discovered he could see directly into the fuselage above him through the torn structure. He reported via intercom that the tail section was wobbling like a fishtail, and that he could count the structural frames still connecting it to the main fuselage. He counted 4. The B-17 was designed with 32 structural frames connecting the cockpit to the tail. The immediate question wasn't whether the aircraft would break apart. The question was when. The decision to keep flying. Ward assessed the situation with brutal clarity. The aircraft was mortally damaged. Attempting to keep it airborne would likely result in structural failure and catastrophic breakup. The sensible decision was to order a bailout immediately while the aircraft was still somewhat stable. But Ward had problems with the bailout. Problem 1. All-American was still overoccupied in France. Bailing out meant capture, interrogation, and imprisonment in stalags for the duration of the war. The crew would survive, but spend years as prisoners. Problem 2. The tail gunner, Sergeant Russell Robinson, reported that his exit hatch was jammed by structural damage. He couldn't bail out. If the crew abandoned the aircraft, Robinson would write it down. Problem 3. Ward wasn't certain the aircraft would break apart. The Boeing engineers had built enormous structural margins into the B-17. The aircraft was still flying, still responding to controls, still maintaining altitude. Maybe, just maybe, it could make it home. Ward made the call. They would attempt to reach England. The crew's response was immediate and practical. They didn't discuss heroism or determination. They discussed physics and engineering. Burrell calculated structural load factors. Bombardier Conda assessed whether jettisoning bombs would reduce stress. Navigator Newsley plotted the shortest course to England, 400 miles over hostile territory and open ocean. Co-pilot Bragg took control while Ward left his seat and inspected the damage personally. Crawling aft through the fuselage, Ward discovered the extent of the destruction. The aircraft was effectively two separate airframes connected by a thread of metal and cable. Any significant stress, turbulence, evasive maneuvers, even aggressive control inputs could sever that thread. Ward returned to the cockpit and explained the situation to Bragg. The aircraft could stay airborne if flown with absolute smoothness. No aggressive maneuvers, no sudden altitude changes, no violent corrections. Essentially, they would glide the damaged bomber across France, maintaining the gentlest possible flight profile while praying the structure held. The alternative was certain capture or death. The choice wasn't difficult. The engineering miracle. What Ward and his crew didn't fully understand was that they were testing the B-17 structural design beyond anything Boeing engineers had anticipated. The aircraft was performing a real-world stress test that exceeded every calculation used during design certification. The Boeing 299 design specification, from which the B-17 evolved, included structural load factors of 3.0 G positive and 1.5 G negative, meaning the airframe could theoretically survive forces 3 times greater than normal flight loads. These factors were calculated assuming an intact structure with all longerons, stringers, and skin panels contributing to load distribution. All-American had lost approximately 70% of its structural strength in the affected section. The remaining 30%, primarily the left longerons and control cables, was carrying loads meant to be distributed across the entire fuselage cross-section. By calculation, this should have resulted in immediate failure. It didn't fail because Boeing engineers had overbuilt everything. The longerons were sized not for calculated maximum loads, but for loads significantly exceeding worst-case scenarios. The connecting fittings were stronger than necessary. The rivet patterns included redundancy beyond structural requirements. Every component had margin built upon margin. This over-engineering was expensive. Each B-17 cost more than contemporary fighters and used aluminum that could have built 3 smaller aircraft. Critics argued the design was wasteful. The accountants wanted lighter structures that met requirements with minimal excess. But the engineers who designed the B-17 understood combat stress differently than accountants. They built margin because they knew combat would test the aircraft in ways that laboratory testing couldn't predict. They built redundancy because they knew damage would eliminate primary systems. They built strength because they knew crews would push the aircraft beyond rated limits when survival demanded it. All-American was flying proof that the engineers were correct. The aircraft was holding together because someone at Boeing had insisted on structural members 20% stronger than calculations suggested necessary. That 20% margin was the difference between catastrophic failure and continued flight. The jury-rigged repair. As All-American crossed the French coast heading toward the Channel, Burrell realized the tail section's movement was worsening. The structure was flexing more severely, and the control cable tension was varying unpredictably. Unless something was done to stabilize the connection, structural failure was inevitable, maybe not immediate, but within the 3 hours needed to reach England. Burrell proposed a solution that was either brilliant or insane. Use parachutes as reinforcement straps to stabilize the tail section. The theory was sound. Parachutes were designed to handle sudden loads during deployment, forces that exceeded the stress currently on the damaged longerons. If parachute shroud lines could be attached to both the main fuselage and tail section, they might provide enough additional support to prevent catastrophic movement. The execution was terrifying. Burrell and other crew members would need to move through the damaged section, secure parachute shroud lines to structural members, and create makeshift tension straps while the aircraft flew at 180 miles per hour at 22,000 feet. One mistake, one slip into the open gap, meant falling through the aircraft and out into space. Burrell didn't ask permission. He gathered 3 parachutes, instructed crew members on the procedure, and moved aft. The process took 40 minutes. Burrell and 2 other crew members, Zuck and waist gunner Sergeant Joseph Kowalski, worked in the damaged section with safety lines attached to intact structural members. They wrapped parachute shroud lines around the remaining longerons, ran the lines across the 6-foot gap, and secured them to the tail section structure. The wind screaming through the gap was so powerful that crew members had to crawl rather than stand. The temperature at altitude was minus 40 degrees Fahrenheit. The noise made communication impossible. They worked by hand signals and shared understanding of the objective. When completed, 8 parachute shroud lines spanned the gap, creating a web of tensioned connections that supplemented the remaining structural attachment. The tail section's movement stabilized immediately. The parachute lines vibrated under load, proving they were carrying significant force, but they held. Burrell returned to the cockpit and reported the repair was holding, but any significant stress would likely snap the shroud lines and sever the remaining structure. Ward acknowledged and made the decision that would define the rest of the flight. They would not deviate from course regardless of threats. Fighter attacks, flat concentrations, navigation errors, none of it mattered. The aircraft would fly the straightest possible line to England because any maneuvering would destroy the jury-rigged repair. The flight across France. The route from Saint-Nazaire to the English coast crossed 200 miles of occupied France. The standard procedure for damaged bombers was to descend to lower altitude where air density provided better engine performance and where crew could survive without oxygen. Ward kept All-American at 22,000 feet because descending would change the aerodynamic loads on the structure. German radar tracked them across France. Luftwaffe controllers, noting the bomber's slow speed and straight-line course, vectored fighters for interception. The Germans assumed the bomber was crippled and vulnerable, easy meat for an aggressive attack. What the Germans didn't know was that Ward had briefed his gunners. They would defend but not provoke. Gunners would fire only when fighters approached within lethal range. The goal wasn't to destroy attackers, but to discourage them without forcing evasive maneuvers that would stress the damaged structure. 3 Messerschmitt 109s intercepted All-American over Brittany. The lead fighter positioned for a standard tail attack closed to 500 yards and opened fire. Tail gunner Robinson returned fire, forcing the 109 to break off. The fighter pilot, perhaps recognizing the bomber's damage and assuming it would crash anyway, didn't press the attack. The formation departed, likely reporting another probable kill. This pattern repeated twice more. Fighters approached, evaluated the damaged bomber, fired briefly, and departed when return fire indicated the defensive armament was still functional. The Germans were conserving ammunition for intact bombers rather than wasting it on an aircraft that looked ready to collapse. Each attack stressed the structure. Each burst of defensive fire from the bomber's guns created recoil that vibrated through the weakened fuselage. Each evasive flinch from Ward's control inputs tested the parachute shroud lines. But the aircraft held together. The jury rig held. The engineering margins held. By the time All-American reached the French coast, it had survived 90 minutes of flight in a condition that should have resulted in immediate structural failure. The crew began to believe they might actually reach England. Then the real challenge began, crossing the English Channel. The Channel crossing. The English Channel, 21 miles wide at its narrowest point, presented the most dangerous phase of the flight. Over land, an emergency landing, while risky, was possible. Over water, ditching a damaged B-17 was nearly certain death. The aircraft would break apart on impact, the severed tail section would separate completely, and crew survival in 50-degree water was measured in minutes. Ward had to decide. Attempt the Channel crossing or turn back and land in occupied France, accepting capture but surviving. Some crew members suggested turning back. The aircraft had proven it could fly. Landing in France would at least guarantee survival in prison camps. Ward's response was direct. "We're going home." The Channel crossing would take 18 minutes at their current speed. 18 minutes of flying over water with an aircraft held together by parachute shroud lines and remaining structural longerons that were stressed beyond design limits. 18 minutes where any structural failure would mean ditching in water too cold to survive. Ward maintained course and altitude. The decision was made. The crew would either make it across or die trying. At 22,000 feet above the Channel, the wind was relentless, 45 miles per hour from the west, creating turbulence that buffeted the damaged bomber. Each gust tested the repair. Each vibration stressed the remaining structure. The parachute shroud lines vibrated visibly, tensioned so tight that Burl could see individual fibers straining. Navigator Newsel provided continuous updates. 15 minutes to English coast, 12 minutes, 10 minutes. The numbers counted down while every crew member watched the structural connection between fuselage and tail, waiting for the moment when the parachute lines would snap and the tail would separate. The tail gunner, Robinson, trapped in his position by jammed hatches, reported he could see clear sky through the fuselage gap above him. He joked via intercom that he had the best view in the Air Force, straight up through the bomber. The humor was gallows humor, acknowledging that he was riding in the section most likely to separate if structure failed. 7 minutes to coast, 5 minutes, 3 minutes. At 6 minutes to English landfall, one of the parachute shroud lines parted. The snap was audible throughout the aircraft, a sharp crack, followed by the sound of fabric whipping in the wind. The tail section's movement increased immediately. flexing more violently as loads redistributed to the remaining 7 shroud lines. Burrell reported the failure to Ward. Ward acknowledged and made no course changes. They were committed. Either they'd make the coast or they wouldn't. Trying to descend prematurely would likely finish the structural failure. 2 minutes to coast. The English coastline was visible ahead, white cliffs and green countryside that represented survival. A second shroud line parted at 90 seconds from landfall. The tail section's deflection increased dramatically. From the cockpit, Ward could see in his mirrors that the tail was moving independently, oscillating up and down with each gust of wind. The remaining 5 shroud lines were carrying all the load. Mathematics and engineering judgment both suggested they would fail within minutes. Ward aimed for the coastline and hoped 5 shroud lines would hold for 90 more seconds. They did. All-American crossed the English coast at 22,000 feet with its tail section still attached, its crew still alive, and its structure still barely intact. The crew cheered, some cried, others prayed. They had survived the channel. Now they just had to land. The landing that shouldn't have worked. Ward's first priority was finding a suitable airfield. All-American was flying at minimum safe speed, 180 miles per hour, significantly slower than normal cruise, because any speed increase would stress the remaining structure. This limited their range. They needed an airfield within 30 minutes flying time. The nearest suitable field was RAF Predannock in Cornwall, a base used for training and emergency landings. Ward radioed ahead. Aircraft severely damaged, structural integrity compromised, requesting emergency landing priority. RAF controllers cleared all other traffic and activated emergency services. Crash crews positioned along the runway. Ambulances waited. Base personnel who witnessed All-American's approach initially thought they were seeing an optical illusion. The aircraft appeared to be in multiple pieces flying in formation. Landing a structurally compromised aircraft requires counterintuitive flying. Ward needed to maintain enough speed to keep control authority but reduce speed enough to land before reaching the end of the runway. The conflict was irreconcilable. Slowing for landing would reduce airflow over control surfaces, decreasing control effectiveness just when he needed maximum control. Maintaining speed for control would result in runway overrun. Ward compromised. He would fly the approach at minimum controllable speed, touch down as gently as possible to avoid structural shock, and accept whatever landing roll resulted. If they overran the runway, at least they'd be on the ground rather than broken apart in mid-air. The approach to Predannock presented final challenges. Wind gusts at low altitude were more severe than at 22,000 feet, causing the tail section to flex visibly. Each deflection tested the remaining parachute shroud lines. Ward could feel the aircraft's flight characteristics changing as tail effectiveness varied with the structural flexing. At 500 feet altitude, a third shroud line parted. The tail section's movement increased dramatically. From the cockpit, Ward could see the entire tail oscillating, up, down, lateral movement that should have destroyed control authority. Yet the aircraft continued responding to inputs. The control cables remained intact despite the movement, testament to their over-engineered strength. Ward crossed the runway threshold at 150 feet altitude. 110 miles per hour indicated airspeed, significantly slower than normal landing speed, but the minimum that still provided control. The approach was perfect, aligned with centerline, descent rate controlled, power managed. At 20 feet altitude, Ward reduced power and flared for landing. The tail section deflected upward as aerodynamic loading changed during the flare. Ward heard fabric tearing, more shroud lines failing, but the tail remained attached. The main wheels contacted the runway simultaneously. The touchdown was smooth, so gentle that observers reported it looked like a routine training landing. Ward held the nose up as long as possible, aerodynamic braking reducing speed while keeping weight off the nose gear. At 90 miles per hour, Ward lowered the nose. The nose gear contacted and held. The aircraft rolled down the runway, slowing through aerodynamic drag and wheel friction. Ward didn't touch the brakes. Brake application would load the structure asymmetrically and could trigger the tail separation. At 60 miles per hour, the fourth shroud line failed, then the fifth, then the last two in rapid succession. The tail section began separating, but the aircraft was rolling slow enough that the structural failure was controlled rather than catastrophic. The tail dragged slightly as the remaining longerons bent, then touched the runway and settled as forward momentum bled away. All-American stopped 5,000 feet down the runway, well within the available 6,000 feet. The aircraft was intact, the crew was alive, and the tail section, while separated on the ground, had remained attached throughout the landing roll. Ward shut down the engines and sat in silence for a moment, then he activated the internal mic. "Everybody out, now." The crew evacuated through all available exits. Robinson, whose hatches had been jammed throughout the flight, was extracted through the tail gunner position by ground crews who cut through the damaged structure. The entire crew was on the ground within 2 minutes. As they walked away from All-American, Burrell turned back to look at the aircraft. The damage was stunning in still photography and from ground perspective. The fuselage was effectively severed, the tail section separated but laying intact behind the main structure. The parachute shroud lines hung limp, their job completed. Burrell's assessment: "I don't know how that airplane flew. Looking at it now, knowing what held it together, I can't believe it stayed in one piece. We should have crashed in France. We should have crashed in the Channel. We should have broken apart during landing. But none of that happened because somebody built that aircraft stronger than it needed to be, and because Lieutenant Ward flew it like he was holding an egg." The men behind the medal. The crew of All-American represented a cross-section of American youth thrust into industrial warfare. Their backgrounds revealed the democratic nature of the bomber campaign. Farm boys and city kids, college graduates and high school dropouts, all trained to operate complex machinery in the most dangerous environment imaginable. James Ward had been studying engineering at the University of Tennessee when war broke out. He enlisted in January 1942, completed flight training in 7 months, and arrived in England in December 1942. His engineering background gave him intuitive understanding of structural mechanics, knowledge that proved critical when assessing whether All-American could survive the flight home. Post-war, Ward returned to Tennessee, completed his engineering degree, and worked for 40 years designing bridges. He never spoke publicly about the flight until the 1980s, when researchers discovered the incident in declassified records. Kenneth Bragg, the co-pilot, was the son of a Dallas oil executive who joined the Army Air Forces against his father's wishes. His wealthy background made him an outsider in the crew initially, but his competence under pressure earned respect. During the flight home, Bragg maintained continuous communication with Ward, managed engine settings to optimize fuel consumption, and handled radio communications with RAF controllers. After the war, Bragg entered politics, serving 2 terms in the state legislature before dying in a car accident in 1967. Dewey Burrell, the flight engineer who conceived and executed the parachute shroud line repair, had been an auto mechanic in rural Georgia before the war. His mechanical intuition, the ability to understand how things worked without formal training, saved the crew. Burrell's decision to use parachutes as structural reinforcement wasn't documented in any manual. It was improvisation born of understanding materials, loads, and the physics of tension. After the war, Burrell opened a garage in Atlanta and never flew again. He told his family the flight on All-American was enough flying for one lifetime. Michael Zook, the radio operator who should have died in the collision, was a first-generation Polish immigrant from Chicago. He'd been at his radio station when the 109 struck. destroying the compartment seconds after he had left it. Zook spent the rest of the flight convinced he was living on borrowed time, that fate had spared him for reasons he didn't understand. After the war, he became a Catholic priest, serving parishes in Illinois for 45 years. In a 1989 interview, he stated, "God moved me forward 3 seconds before that fighter hit. I don't know why I was spared, but I spent my life trying to justify that gift." Russell Robinson, the tail gunner trapped in his position throughout the flight, was a 19-year-old farm boy from Iowa. He'd never been more than 50 miles from home before enlisting. During the flight, Robinson could see the parachute shroud lines through the gap in the fuselage, watch them stretch and vibrate under load, and calculate how little held him to the rest of the aircraft. After landing, Robinson requested immediate transfer to ground duty. His request was denied. The Air Force needed experienced gunners. He completed his combat tour, survived 23 more missions, and never flew again after returning to the United States. He died in 2003 at age 79, having spent 60 years with recurring nightmares about tail sections separating from bombers. The other crew members, Bombardier Elton Conda, Navigator Harry Nusel, ball turret gunner Samuel Sarkopolis, waist gunners Joseph Kowalski and Tony Marchioni, and nose gunner George Ike, returned to combat duty within a week. They flew together for 2 more months before being split up and assigned to different crews as the 97th Bombardment Group expanded. 6 of the 10 survived the war. 4 were killed in action on subsequent missions, their names now inscribed on memorial walls in Normandy and Cambridge. The investigation. Within hours, Boeing engineers arrived at Predenac to examine All-American. The damage assessment would inform future design decisions and structural reinforcement programs. More immediately, Boeing needed to understand how an aircraft could survive damage that should have resulted in catastrophic structural failure. The examination revealed the extent of the miracle. The right side of the fuselage was completely removed from bulkhead 5, behind the cockpit, to bulkhead 10, tail section attachment point. This represented a loss of 100% of right side skin panels, 100% of right side longerons, primary structural members, 100% of right side stringers, secondary structural support, 75% of horizontal cross members, 50% of vertical stabilizer attachment structure. What remained was left side longerons, primary structure, control cables running through left side of the fuselage, partial floor structure, parachute shroud lines, jury rig repair. Boeing engineers calculated that the remaining structure was supporting approximately 300% of its design load during flight. The left longerons should have failed under this stress. They didn't fail because the engineering margins exceeded worst-case calculations. The investigation revealed design decisions that saved the aircraft. The longerons were manufactured from 7075 T6 aluminum alloy with yield strength of 73,000 psi, higher than necessary for calculated loads. The cross-sectional area of each longeron was 20% larger than minimum structural requirements. The rivets connecting longerons to cross members were spaced at intervals calculated for loads 150% greater than maximum predicted stress. Every over-engineered decision contributed to survival. Every wasteful margin justified its cost. The accountants who'd questioned the expenses were wrong. The conservative engineers who'd insisted on excessive strength were vindicated. Chief Engineer Claire Edgevet, who'd overseen B-17 design, reviewed the damage assessment and wrote in a memo to Boeing President Philip Johnson, "All-American proves our design philosophy. We built the B-17 heavy because we didn't know exactly how combat would stress the airframe. We included margin because we couldn't predict every failure mode. We overbuilt because crew lives justified the cost. This aircraft survived damage that exceeded our worst-case assumptions because we designed beyond our calculations. That approach is expensive, it's also correct. The memo was dated April 15, 1943. Boeing used the All-American incident in internal training, teaching new engineers that conservative design saved lives when operations exceeded predictions. The philosophy influenced B-29 Superfortress design, B-47 Stratojet development, and eventually the B-52, an aircraft so over-engineered that bombers built in the 1950s remain operational 70 years later. The comparative context. All-American survival was exceptional but not unique among B-17s. The Flying Fortress accumulated dozens of similar incidents throughout 1943-1945, where aircraft absorbed catastrophic damage and returned to base. These cases built the B-17's legendary reputation for survivability. On February 1, 1943, B-17F Shoo Shoo Baby returned to base with its No. 3 engine completely missing, not damaged, but torn from the wing by flak, leaving an empty nacelle and exposed wing structure. The aircraft flew 300 miles on 3 engines with severe asymmetric thrust and landed successfully. On April 17, 1943, B-17F Batlin Betty collided with another B-17 over Germany, losing 6 feet of its left wing. The pilot compensated for asymmetric power and aileron trim, flying the unbalanced bomber 400 miles to England. On October 8, 1943, B-17F Hell's Angels was struck by flak over Bremen, receiving damage that severed half the tail section's connecting structure. The pilot flew home with the tail flexing independently, much like All-American, but with less severe damage. The pattern repeated throughout the war. B-17s returned with engines gone, tails damaged, wings perforated, control surfaces missing. The accumulation of survival stories created mythology around the aircraft's toughness, mythology that proved accurate under analysis. Statistical studies conducted by the 8th Air Force in 1944 quantified B-17 survivability. Aircraft that sustained heavy damage had a 65% probability of returning to base if the pilot maintained control immediately after damage. Comparable statistics for B-24 Liberators showed 42% survival probability. Lancaster bombers, 38%, and Halifax bombers, 35%. The B-17 structural margin translated directly into crew survival rates. German intelligence recognized this disparity. A Luftwaffe report from July 1943 specifically noted, "The American B-17 requires significantly more ammunition to destroy than other heavy bombers. Average ammunition expenditure to destroy B-17, 22 20mm cannon hits. Average for B-24, 11 hits. Average for Lancaster, 9 hits. Conclusion: B-17's structural strength exceeds other designs. Recommend concentrated fire on engines and control surfaces rather than fuselage." The recommendation was implemented, but it didn't solve the problem. The B-17's engines were radial air-cooled designs that could survive hits that would destroy liquid-cooled engines. The control surfaces were redundantly powered with backup systems. Even when German fighters followed the recommended tactics, B-17s continued surviving damage that destroyed other aircraft. This survivability came at a cost. The B-17 was heavier than competitors, carried less payload, and required more maintenance. But crews trusted it, and that trust affected mission effectiveness. Pilots flew more aggressively knowing the aircraft could absorb damage. Crews maintained morale through difficult missions because they believed in their aircraft's strength. The psychological advantage was as valuable as the structural advantage. The production philosophy. The engineering margins that saved All-American originated in Boeing's production philosophy, a deliberate decision to build aircraft stronger than minimum requirements despite higher costs and resource consumption. Boeing produced 12,731 B-17s between 1941 and 1945. Each aircraft required 14,000 pounds of aluminum, 2,400 pounds of steel, 1,100 pounds of copper and brass, 650 pounds of rubber, 65,000 individual parts, 360,000 rivets, and 8 miles of electrical wiring. The manufacturing process involved 42 major assembly stations, 18 sub-assembly lines, and quality control inspection at 127 checkpoints. Each checkpoint verified dimensions, material specifications, and structural integrity. Rejection rates averaged 3%, meaning 3 out of every 100 components were rejected for not meeting standards that already exceeded minimum requirements. This quality control was expensive. Boeing employed 30,000 workers at its Seattle plant by 1944, producing 4 B-17s daily. Competitor Douglas Aircraft employed 22,000 workers, producing 8 A-20 attack bombers daily, twice the output with fewer workers. The efficiency difference reflected the B-17's complexity and Boeing's insistence on quality over speed. Critics argued Boeing should simplify the design to increase production. Engineer Ed Wells, supervising B-17 production, refused. "We're building aircraft that will be shot at by the most advanced weapons Germany can deploy. We're sending them into combat with 10 men aboard. Those men deserve the best aircraft we can build, not the cheapest or the fastest to produce. If that means we build fewer bombers, so be it. The crews who fly them will survive at higher rates, and that's worth the cost." The statistics proved Wells correct. The 8th Air Force flew 291,508 B-17 combat sorties between 1942 and 1945, losing 4,735 aircraft to all causes, a loss rate of 1.6%. The B-24 Liberator, produced in greater numbers, 18,482 total, and at lower cost, flew 226,775 sorties and lost 3,626 aircraft, a loss rate of 1.6%. The rates appeared equal, but the nature of losses differed. B-17s lost to mechanical failure, 358 aircraft, or 7.6% of total losses. B-24s lost to mechanical failure, 891 aircraft, or 24.6% of total losses. B-17s lost to combat damage but recovered to base, 2,118 aircraft returned despite damage classified as total loss. B-24s recovered with comparable damage, 892 aircraft. The B-17's over-engineered structure meant more aircraft survived to fight another day. The production efficiency sacrificed in favor of quality translated into operational effectiveness when measured correctly, not by aircraft produced, but by missions completed and crews returned. The physics of survival. The aerodynamic principles that allowed All-American to continue flying with severed fuselage defied intuitive understanding. Aircraft stability depends on the relationship between center of gravity and center of lift. Structural damage typically disrupts this relationship catastrophically. All-American's survival depended on 3 factors. First, the damage was located behind the center of gravity. The tail section's mass represented only 8% of total weight. Losing structural connection to the tail reduced the aircraft's moment of inertia but didn't shift the center of gravity forward significantly. Ward could maintain control because the aircraft remained balanced around its center of mass. Second, the control cables remained intact. Despite the fuselage severance, the elevator and rudder controls routed through the left side of the fuselage maintained continuity. Ward could still command pitch and yaw control even though the structural connection between controls and surfaces was compromised. Third, the parachute shroud line repair provided just enough rigidity to prevent catastrophic tail oscillation. Without that repair, the tail section would have begun oscillating in phase with airflow disturbances, a phenomenon called flutter that destroys aircraft within seconds. The shroud lines damped the oscillations enough to keep flutter from developing. Dr. Theodor von Karman, director of the Guggenheim Aeronautical Laboratory at Caltech, reviewed the All-American incident in 1945 as part of a study on aircraft structural failure modes. His analysis concluded, the aircraft survived through a fortunate combination of damage location, control system redundancy, and improvised structural reinforcement. Any one factor absent would have failed. The probability of all three factors aligning favorably is approximately 0.003, 3 chances in 1,000. The crew experienced extraordinary luck combined with competent improvisation. Von Karman's analysis understated the engineering contribution. The luck of damage location behind the center of gravity was really the luck of Boeing engineers placing heavy components forward. The luck of control cables surviving was really the result of Boeing routing redundant control systems through both sides of the fuselage. The luck of successful improvisation was really the result of Boeing building a structure strong enough that parachute shroud lines could supplement it. Luck favors the well-engineered. The German perspective. Luftwaffe intelligence collected extensive data on B-17 combat damage throughout the war. The All-American incident was noted in reports compiled by Oberst Josef Pips Priller, commanding officer of Jagdgeschwader 26, the unit whose pilot had collided with the aircraft. Priller's report, dated April 15, 1943, stated, Oberleutnant Girth succeeded in his attack against an American heavy bomber, achieving a direct hit that severed the aircraft's fuselage. Multiple witnesses confirm the bomber's tail section was attached only by minimal structure. Girth was killed in the attack, his sacrifice credited as a probable kill. However, subsequent intelligence indicates the damaged bomber may have reached England. If confirmed, this represents exceptional structural strength that exceeds our current understanding of American heavy bomber design. The report continued with technical analysis. The American B-17 appears designed with structural redundancy that allows continued operation despite catastrophic damage. Previous intelligence assumed the aircraft's heavy construction was an inefficient design. Current data suggests the heavy construction is deliberate over-engineering to ensure survival despite combat damage. Recommendation: reevaluate American engineering philosophy. Their approach sacrifices efficiency for survivability. In a sustained air campaign, survivability may prove more valuable than efficiency. The recommendation was forwarded to Reich Marshal Hermann Göring, who dismissed it. Göring believed German fighters were technically superior and that American heavy bombers would be defeated through superior tactics rather than needing weapons development. This decision, dismissing intelligence that American engineering philosophy differed fundamentally from the German approach, contributed to the Luftwaffe's eventual defeat. German pilots who'd attacked All-American and seen it survive were interviewed after the war. Unteroffizier Hans Berger, one of the Me-109 pilots who'd made firing passes at the damaged bomber, stated in 1946, "We saw the aircraft was cut nearly in half. We saw the tail moving independently from the fuselage. We assumed it would fall apart at any moment. We fired at it more from curiosity than necessity. We wanted to see what would finally break it. Nothing we did mattered. The bomber kept flying. I remember thinking, if the Americans build all their aircraft like this, we've already lost." Berger's assessment was correct. By mid-1943, American industrial capacity was producing bombers faster than Germany could destroy them, and those bombers were tough enough to survive damage that would destroy German aircraft. The combination of quantity and quality created an equation Germany couldn't solve. The strategic impact. All Americans' survival, while dramatic, was tactically insignificant. One bomber reaching home instead of crashing changed nothing about the war's trajectory. But the incident's strategic impact was substantial. It proved the B-17's durability in conditions that exceeded any previous damage reports, validating Boeing's design philosophy and justifying continued B-17 production, despite pressure to switch to newer designs. By April 1943, the Air Force was debating bomber priorities. The B-24 Liberator offered longer range, higher service ceiling, and greater payload capacity. Some planners argued that B-17 production should cease in favor of B-24 mass production. The All-American incident provided concrete evidence that the B-17's structural advantages justified its continued production despite pressure to switch to newer designs. General Henry Hap Arnold, commanding the Army Air Forces, received Boeing's damage assessment on April 20, 1943. His response memo, dated April 22, stated, "The B-17's survival of fuselage severance proves its structural superiority beyond question. While the B-24 offers operational advantages, the B-17's ability to absorb punishment and return crews safely is strategically valuable. Recommendation: continue B-17 production at current levels. The aircraft has proven itself under conditions that would destroy other designs." Arnold's decision ensured B-17 production continued through the war's end. The 8th Air Force ultimately operated both B-17s and B-24s in roughly equal numbers, but the B-17's reputation for survivability meant it was preferentially assigned to the most dangerous missions: deep penetration raids, heavily defended targets, and missions where survival rates were lowest. The irony was perfect. The B-17's toughness meant it was sent into the most dangerous situations, which produced more damage, which further proved its toughness, which justified sending it into even more dangerous situations. The cycle was brutal but effective. Crews flying B-17s had higher survival rates even on the most dangerous missions. The aftermath. All-American never flew again. The damage was too extensive for economical repair. The aircraft was surveyed, stripped of usable components, and scrapped. Serial number 41-24406 was removed from operational inventory in May 1943. The crew received no medals for the flight. Ward was not recommended for the Distinguished Flying Cross or other valor decorations. The mission was classified because the B-17's structural capabilities were valuable intelligence that should not be revealed to German engineers. If the Luftwaffe understood exactly how much damage a B-17 could survive, they might develop weapons or tactics specifically designed to exploit remaining vulnerabilities. The classification lasted until 1959, when Air Force historians reviewing wartime records discovered the incident and began documenting it. By then, most of the crew had returned to civilian life and were difficult to locate. Ward was contacted in 1960 and asked for an interview. He declined, stating simply, "We did our job. That's all there is to say." The crew completed their combat tours with varying outcomes. Ward flew 23 additional missions before rotating home in August 1943. He accumulated 350 combat hours, survived 31 missions, and never again experienced damage comparable to All-American. After the war, he worked as a structural engineer in Tennessee, designing bridges and buildings until retiring in 1985. He died in 1991 at age 72, having rarely spoken about his military service. Bragg completed 25 missions before being killed on his 26th mission during a raid on Schweinfurt in October 1943. His B-17 was hit by flak, caught fire, and exploded before the crew could bail out. He was 23 years old. Burrell survived 29 missions and rotated home in September 1943. He returned to Georgia, opened his automotive garage, and lived quietly until he died in 2001 at age 79. His family discovered after his death that he'd kept detailed notes on the All-American flight, including sketches of the parachute shroud line repair. The notes are now preserved at the National Museum of the United States Air Force. Zach completed 32 missions, received the Distinguished Flying Cross for actions unrelated to the All-American flight, and returned to the United States in November 1943. He entered seminary in 1944 and was ordained in 1948. He served as a Catholic priest for 45 years before retiring in 1993. He died in 2008 at age 86, having written extensively about how his near-death experience on All-American shaped his religious vocation. Robinson completed 24 missions despite his request for transfer to ground duty. He was discharged in March 1944 after accumulating enough points for rotation. He returned to Iowa, farmed for 50 years, and never spoke publicly about his war service. His family learned about the All-American flight only after his death when reviewing his military records. Of the 10 crew members, 6 survived the war. 4 were killed in action on subsequent missions, casualties of the brutal attrition that characterized strategic bombing campaigns. Their names are inscribed on memorial walls in Normandy and Cambridge, remembered as statistics in the vast accounting of aerial warfare. The museum display. Today, a detailed scale model of All-American sits in the National Museum of the United States Air Force in Dayton, Ohio. The model shows the aircraft in its damaged state, fuselage severed, parachute shroud lines visible, tail section attached by threads of metal and fabric. A placard beside the model tells the story in 200 words, a sanitized summary that can't capture the full scope of what occurred. The real aircraft was scrapped in 1943, its components recycled into other bombers. No physical remnant remains, except photographs taken at Predonic after landing. Those photos show an aircraft that appears to be in multiple pieces, the damage so extensive that viewers initially assume they're seeing wreckage of a crash rather than an aircraft that flew 400 miles and landed successfully. The striking photograph shows Ward and his crew standing beside the damaged aircraft, posing for the camera as they've just completed a routine training flight. Their expressions show exhaustion mixed with disbelief. They're alive. The aircraft is on the ground. The impossible has occurred, and they're trying to process what they've just experienced. At the bottom of the museum placard is a quote from Ward, recorded during a 1985 interview. "We flew that bomber home because quitting wasn't an option. The Germans had cut our aircraft in half, but they hadn't cut our determination. Every man on that crew stayed at their post, did their job, and trusted that Boeing had built the aircraft strong enough to get us home. Turns out they did. Boeing engineers somewhere in Seattle had decided to make those longerons a little thicker than necessary, and that decision saved our lives. I never met those engineers, but I owe them everything." The quote captures the essence of All-American's story, the intersection of human determination and engineering excellence, where both were necessary and neither alone would have succeeded. The engineering legacy. The All-American incident influenced post-war aircraft design in ways both obvious and subtle. Boeing engineers used the data to validate their structural design philosophy and applied those lessons to subsequent aircraft. The B-29 Superfortress, entering service in 1944, incorporated structural lessons learned from B-17 combat damage reports. The longerons were sized with even greater margins. The control systems included triple redundancy. The pressurization structure was designed to maintain integrity despite battle damage. These decisions made the B-29 heavier and more expensive than necessary by pure calculation, but they saved crews throughout the Pacific Campaign. The crew completed their combat tours with varying outcomes. Ward flew 23 additional missions before rotating home in August 1943. He accumulated 350 combat hours, survived 31 missions, and never again experienced damage comparable to All-American. After the war, he worked as a structural engineer in Tennessee, designing bridges and buildings until retiring in 1985. He died in 1991 at age 72, having rarely spoken about his military service. Bragg completed 25 missions before being killed on his 26th mission during a raid on Schweinfurt in October 1943. His B-17 was hit by flak, caught fire, and exploded before the crew could bail out. He was 23 years old. Burrell survived 29 missions and rotated home in September 1943. He returned to Georgia, opened his automotive garage, and lived quietly until he died in 2001 at age 79. His family discovered after his death that he'd kept detailed notes on the All-American flight, including sketches of the parachute shroud line repair. The notes are now preserved at the National Museum of the United States Air Force. Zoc completed 32 missions, received the Distinguished Flying Cross for actions unrelated to the All-American flight, and returned to the United States in November 1943. He entered seminary in 1944 and was ordained in 1948. He served as a Catholic priest for 45 years before retiring in 1993. He died in 2008 at age 86, having written extensively about how his near-death experience on All-American shaped his religious vocation. Robinson completed 24 missions despite his request for transfer to ground duty. He was discharged in March 1944 after accumulating enough points for rotation. He returned to Iowa, farmed for 50 years, and never spoke publicly about his war service. His family learned about the All-American flight only after his death when reviewing his military records. Of the 10 crew members, 6 survived the war. 4 were killed in action on subsequent missions, casualties of the brutal attrition that characterized strategic bombing campaigns. Their names are inscribed on memorial walls in Normandy and Cambridge, remembered as statistics in the vast accounting of aerial warfare. The museum display. Today, a detailed scale model of All-American sits in the National Museum of the United States Air Force in Dayton, Ohio. The model shows the aircraft in its damaged state, fuselage severed, parachute shroud lines visible, tail section attached by threads of metal and fabric. A placard beside the model tells the story in 200 words, a sanitized summary that can't capture the full scope of what occurred. The real aircraft was scrapped in 1943, its components recycled into other bombers. No physical remnant remains, except photographs taken at Perdonic after landing. Those photos show an aircraft that appears to be in multiple pieces, the damage so extensive that viewers initially assume they're seeing wreckage of a crash rather than an aircraft that flew 400 miles and landed successfully. The striking photograph shows Ward and his crew standing beside the damaged aircraft, posing for the camera as they've just completed a routine training flight. Their expressions show exhaustion mixed with disbelief. They're alive. The aircraft is on the ground. The impossible has occurred, and they're trying to process what they've just experienced. At the bottom of the museum placard is a quote from Ward, recorded during a 1985 interview. "We flew that bomber home because quitting wasn't an option. The Germans had cut our aircraft in half, but they hadn't cut our determination. Every man on that crew stayed at their post, did their job, and trusted that Boeing had built the aircraft strong enough to get us home. Turns out they did. Boeing engineers somewhere in Seattle had decided to make those longerons a little thicker than necessary, and that decision saved our lives. I never met those engineers, but I owe them everything." The quote captures the essence of All-American's story, the intersection of human determination and engineering excellence, where both were necessary and neither alone would have succeeded. The engineering legacy. The All-American incident influenced post-war aircraft design in ways both obvious and subtle. Boeing engineers used the data to validate their structural design philosophy and applied those lessons to subsequent aircraft. The B-29 Superfortress, entering service in 1944, incorporated structural lessons learned from B-17 combat damage reports. The longerons were sized with even greater margins. The control systems included triple redundancy. The pressurization structure was designed to maintain integrity despite battle damage. These decisions made the B-29 heavier and more expensive than necessary by pure calculation, but they saved crews throughout the Pacific campaign. The B-47 Stratojet, America's first swept-wing jet bomber, used structural design principles traceable to B-17 experience. The wing spars were sized to support loads 200% greater than the maximum predicted stress. The fuselage frames included redundant load paths. The control cables were tripled throughout. These margins made the B-47 heavier than necessary, but ensured survival when unforeseen stress occurred, including several incidents where B-47s survived mid-air collisions and structural failures that should have been catastrophic. The B-52 Stratofortress represents the ultimate vindication of conservative engineering philosophy. Designed in the 1950s using slide rule calculations and conservative safety factors, the B-52 was built with structural margins that seemed excessive even then. 70 years later, B-52s remain operational, their airframes accumulating stress cycles that far exceed original design predictions. They survive because someone at Boeing in 1952 insisted on building them stronger than necessary. This design philosophy extended beyond military aviation. Commercial airliners adopted similar conservatism after several high-profile crashes in the 1950s revealed the consequences of optimized to minimum structures. Modern airliners are designed with load factors, redundancy, and safety margins that trace directly to lessons learned from aircraft like the B-17. That over-engineering justifies its cost when measured in lives rather than dollars. The final assessment. The flight of All-American on April 1, 1943, lasted 3 hours and 40 minutes from collision to landing. During that time, the crew demonstrated 10 men maintaining composure during a crisis that justified an immediate bailout. Improvised structural repair using materials never intended for that purpose. Flight discipline, maintaining smooth control inputs despite stress and fear. Navigation across hostile territory without deviation despite fighter attacks. Landing approach and touchdown executed with precision despite structural instability. The aircraft demonstrated structural margins exceeding design calculations by orders of magnitude. Engineering conservatism that anticipated unpredictable combat damage. Design philosophy prioritizing crew survival over cost optimization. Manufacturing quality, maintaining tolerance standards under catastrophic stress. The result: 10 men survived who should have died. 1 aircraft landed that should have crashed. Proof that over-engineering justifies its cost when measured in lives rather than dollars. The broader lessons. Conservative engineering saves lives when operations exceed design assumptions. Structural margin is valuable insurance against unpredictable circumstances. Crew determination can push equipment beyond rated limits when survival demands it. Design philosophy matters. Building for worst-case scenarios enables survival in cases beyond worst. The final truth. On April 1, 1943, German Oberleutnant Werner Goethe collided with an American bomber and died instantly, confident his final act would destroy the enemy aircraft. His sacrifice was recorded as a probable kill. His name was honored in the Luftwaffe memorial rolls. His family received notification that he died in combat, striking a decisive blow against the enemy. He never knew he'd failed. All-American didn't crash. It flew 400 miles with its fuselage cut nearly in half, crossed the English Channel, held together by parachute shroud lines and engineering margins, and landed successfully with all crew surviving. The Americans returned to combat. The aircraft was scrapped. The mission continued. And somewhere in Seattle, Boeing engineers who'd insisted on building them stronger than necessary saved 10 lives without ever knowing their conservative decisions had been tested to the absolute limit and had succeeded. Ward and his crew never became famous. Their story remained classified for decades. When finally revealed, it was overshadowed by more dramatic tales: fighter races, strategic campaigns, decisive battles. A single bomber limping home didn't fit the narrative of aerial warfare as conquest and glory. But All-American's flight represented something more fundamental than combat heroics. It represented the moment when human will, crew discipline, and engineering conservatism combined to achieve what calculations said was impossible. It proved that determination could overcome physics when margins allowed, that improvisation could supplement design when necessity demanded, and that 10 men working together could save themselves when doctrine said they were already dead. The Germans laughed at American bombers in 1942, calling them slow, ungainly, and inefficient. By 1943, Luftwaffe pilots stopped laughing when they discovered those bombers wouldn't die even when cut in half. All-American flew home because someone at Boeing built it strong enough to survive the impossible. Because 10 men refused to accept that impossible meant certain. Because a farm boy flight engineer understood that parachutes could reinforce longerons. Because a pilot from Tennessee flew 3 hours without a single mistake. Because crew members stayed at their posts in an aircraft that was breaking apart around them. The aircraft that shouldn't have flown landed safely. The crew that should have died survived. And the engineering margins that seemed wasteful proved priceless when tested by reality that exceeded every prediction. At the National Museum of the United States Air Force, visitors walk past the All-American model daily. Most glance at it briefly, note the damage, and continue to more famous exhibits. The story placard is too long for most to read completely. The technical details are incomprehensible to visitors without engineering background. But occasionally, someone stops and studies the model carefully. They look at the severed fuselage, the parachute shroud lines, and the tail section that shouldn't have remained attached. They read the placard completely, they study the photographs, and they understand what they're seeing. They're looking at proof that impossible is just difficult, that nobody's solved yet. That determination plus engineering equals survival. That overbuilding saves lives when those lives depend on margins nobody predicted would matter. They're looking at All-American, the bomber that flew with no fuselage, the crew that refused to die, and the engineers who built just enough extra strength to bridge the gap between probable death and miraculous survival. The aircraft landed, the crew survived, the thunder spoke, and impossible became history.